Hello, everyone. Welcome to Penn's Power Corner. I'm your host, Editor-in-Chief of Power Electronics News, Aalyia Shaukat. So today we'll be speaking with Laurence McGarry, Director of Product Line Management at pSemi, and we'll be talking about the company's Adiabatic switching technology and amongst other things. So thank you for joining me, Laurence. How are you doing today?
Great, thank you, Aalyia. Nice to see you again.
Nice to see you again, too. So, as I was saying earlier, bear with me while I frame the conversation. I've got a bit of a long, introduction. So, I've done a bit of research on pSemi's adiabatic charge pump technology, and it seems pretty foundational to many of pSemi's power management ICs. I read the how-to power white paper and the Bodos article, and they're both very well written. There's a lot of information there. So, from what I understand, you've got your classical charge pump, which is nice for space-constrained smartphones because it removes the bulky inductor that, in buck converters. It also offers a high efficiency, particularly at high conversion ratios where a buck converter may struggle. And that's useful for protocols like fast charging protocols like USPD and PPS. But you still lose efficiency because of charge redistribution losses. So pSemi actually uses small inductors to smooth this charge redistribution by, and I quote, allowing the current to resonate between capacitors to eliminate charge redistribution losses. So just help me fill in the blanks here. Am I missing anything?
I think you got the gist of it actually.
Okay.
So you mentioned charge pumps in mobile applications. Actually, charge pumps can be used in many different applications as well, where you're looking for very high efficient power delivery, particularly in small, low profile applications. To answer your question, one of the potential disadvantages of a charge pump is that if you think about shorting, what you're doing when you're using a charge pump, you're transferring energy between one capacitor and another. And when you short capacitors together of different potential voltages, you will lose energy. And that's called the redistribution loss. So for example, if you have one capacitor at a potential of V and one capacitor at a potential of 0, if you short them together instantaneously, you will lose half the energy of the transfer. So what we do a bit differently at pSemi is if we connect usually a very small chip inductor between the capacitors. And what that does is, if you think about an L and the C, it creates a resonant circuit.
Right.
So instead of that short circuit, that kind of spiky current, which can also cause EMI issues as well and potential disruption at system level, it smooths the current, but it also allows the transition to resonate. So it's a lossless resonant circuit. So essentially, you're turning a very lossy event, if you like, into a lossless event, and you can recover that energy. So that's really what the adiabatic inductor is doing. The losses associated with a charge pump, you've got your major losses are the on losses, but you also have switching losses. And what we're doing here is we're basically reducing or completely eliminating the switching loss.
Thank you. That's very helpful. So, there's 250 plus patents related to the technology. And, when your literature describes the adiabatic inductor as, allowing current to resonate between capacitors, what does that mean for the controller? How does it manage things dynamically, say at very light loads or very heavy loads?
It doesn't mean a huge amount for the controller, really. I mean, we have many controllers. They usually interleave those two phases of the charge pump, or two charge pumps, if you like, operating in parallel, 180 degrees out of phase. So these controllers, or actually, you could call them regulators because they have the FETs integrated.
Okay.
They can work with the inductive element, the adiabatic inductor on the output, or they can work without. Just that without, in most cases, you will see a slight deterioration in the efficiency. So when if you carefully set the parameters of the inductor and the output cap and the parameters of the resonant circuit and the switching frequency of the controller, you will get an improvement in efficiency through the adiabatic performance. So actually no real kind of specific nuance associated with the controller. It will actually work in both situations. But what you do have to get right is it has to be able to modify the switching frequency, and also you've got to kind of set your components, your fly cap components, and your resonant adiabatic and output cap components as well, to make sure that you do get the right resonance and get the right reduction in losses.
Well, then I'll shift to the next question. So multi-level converters, that's in the pSemi's portfolio. How does pSemi marry its adiabatic charge pump technology with multi-level buck converters to deliver a high efficiency despite a high conversion ratio, all within that sort of sub 1 millimeter profile? And I imagine the small inductors have to do with that.
It's a good question, and there's many different answers to that question. I would say from a marketing point of view, I think both appeal and target very similar markets, in the sense that they both target very low profile applications where you've got very small inductors on the output. And where you want to deliver quite significant amounts of current or power to your load in a very efficient way. So they target similar markets. They are the charge pump. You could almost we look at it internally as almost like being a distant relative of the multi-level. I would say the multi-level could almost be considered as an evolution of the charge pump. The charge pump, of course, doesn't regulate. It's an open loop system. So it's like it can be considered like a DC transformer. Whatever you put into the input, you will get at the output, just divided down by the ratio. And that does, as I say, the adiabatic inductor is used in that application. But as you move to multi-level, the big difference is the multi-level is more of a member of the buck family, buck regulator family. So the big difference is it regulates the output. So the inductor is actually there. The output inductor is there for really a different reason. It's really filtering the output. Now, the big advantage, I think, the big advantage of multi-level, it's definitely a more complicated system than a traditional or simple buck converter. You've got a lot more switches. But the big advantage is that the input to the inductor on the, people might call it the LX or VX node on the switches, that voltage is would usually in a traditional buck converter, you would see the full input voltage, plus quite a lot of reverse leakage from the inductor itself. In the multi-level, for example, we've introduced the 4-level converter to the market. And the big advantage of the 4-level is at that node, you only see 1/3 of the input voltage. So you see a much lower voltage exposure across the inductor, to the input of the inductor and across the inductor. So that allows you to reduce the size and the magnitude of the inductance significantly. And you can, again, deliver very efficient power delivery at fairly high power levels into very, very low profile applications. Typically we advertise at sort of 1 millimeter in height. So you're looking at things like smartphone, tablets, and so on. So they are related, but kind of somewhat distantly.
Yeah. The Bodos article kind of covered that. It went into multi-layer buck converters, and then pSemi's technology as well. So pSemi is now a Murata company, which it seems to be quite serendipitous considering Murata is a market leader in MLCCs, and pSemi makes also makes charge pumps. So has pSemi been able to take advantage of this, and are there any tangible benefits that you might be able to share?
pSemi's actually been a Murata company since 2014, so about over 12 years or so. What might be in 2017, pSemi actually acquired a company called Arctic Sand, which is where a lot of the charge pump technology comes from. There's been enormous advantages. In fact, I wouldn't say it was in any way accidental that Murata pSemi bought Arctic Sand. It was actually very much part of a strategy. Murata obviously prolific in capacitors and various types of capacitors from MLCC and so on. The acquisition was because the the energy transfer was based on capacitive energy transfer. So they could realize the synergies between the two companies, between Murata capacitance technology and the ICs. Now, that all said, to answer your question, we tend to, Murata has such a broad kind of prolific range of capacitance that we work with them pretty closely, but we don't really see the need to define new capacitors or different capacitors. Where we kind of add value is when we work together, and our power technologies from charge pump to two-stage regulator to ML multi-level, where we can harness the energy of their capacitors in that energy transfer process to provide high efficiency power delivery.
Okay, thank you. That was helpful. I didn't get that timeline right originally. So 2014 Murata and 2017 Arctic Sand.
Hopefully answered the question. Sorry.
It did very much. Thank you. No, that's a big clarification for me. So thank you. So maybe we could zoom into a flagship, power management IC, the PE 26100, right? Specifically, and how does this represent a culmination of everything that you've just described? So what would it enable for smartphone OEM that may not have been possible before?
Okay. Hopefully quite a lot. So the 26100 or P26100, it's a multi-level converter. It's a 4-level converter, targeting, as I said earlier, kind of smartphone, tablet, very low-profile applications. It's extremely flexible, and I'll maybe talk about that in a second. But one of the things that we perceive in the industry is that mobile phones no longer ship with the cable or the adapter in the box. So you depend on plug-in adapters that you get around your house, around your office, in your car, whatever. So there's this kind of plethora of different adapters that have got to be compatible. And customers, consumers, you and I, we often pick up the closest adapter and we plug it in and we expect fast charging. We expect the same performance from the what's printed on the label or what's printed on the internet. And we often don't get it. And that leads to a lot of frustration from a consumer point of view, because they fundamentally don't understand it. They don't understand why. What our product does is it's very adaptable. For example, it can work at higher input voltages. If you're using a USB 18 volts, so you get a Qi 2.2 from 18 volts adapter, we'll operate in 4-level conversion, for example. If that voltage then goes down to, let's say, 9 volts, a 9-volt adapter, or maybe even a 15-volt adapter, the customer can change that to 3-level operation, and what allows them to optimize the type of circuit that they're deploying at the time, to maximize the efficiency and the power delivery, so they can maximize their charging at that time. The other interesting thing about the multi-level, and this gets back to the relationship between multi-level and charge pump, is a 4-level can actually operate as a divide by 3, and a 3-level can operate as a divide by 2 charge pump. So it's somewhat interchangeable. So if you have a fixed input voltage, you can switch it into charge pump mode, and again provide very efficient energy delivery. So in summary, what the device does is it can be adapted to the type of source that's being applied, the type of adapter or wireless charging source that's being applied, and actually optimize the efficiency so that you maximize the charging and reduce, obviously, the charge time of the phone. So that's the real kind of benefit of our technology. It's to try and reduce or eliminate the confusion around the source adapter.
So so that we could talk about the robotics pivots a little bit. So pSemi announced the P25304 for humanoid robotics, and the IC targets actuators from a 48-volt input architecture. So fast charging and humanoid robotics, they seem like different markets, and I wanted to know what the common thread was in pSemi's capacitive switching that makes it applicable to both markets.
Yeah, I think I kind of mentioned it at the very beginning, it's charge pumps are not just for mobile phones. They are, appropriate for different applications. And we find, from data center to robotics, and even laptops now are looking at charge pumps. the thing that they all have in common is they're looking for smaller space, lower profile, high power delivery that's very very energy efficient. So the losses are very small. So the charger, the multi-level charger is a charger. It's, if you think about it on the kind of source side of the battery, charging the battery. This device that we're talking about, the PE25304, is on the kind of downstream of the battery. So it's converting from 48 to 12. We have another device which can converts from 48 to 24 as well. And the difficulty in robotics, generally you would think about robotics, the body as having quite a lot of space and area. But as you get towards the hand and arm area, it's actually very high density, expensive real estate for electronics. So the charge pump plays in there because you've got, again, very small size, very low profile with high power delivery. So a couple of these modules connected in parallel would be able to deliver, over 150 watts, for example. The other advantage that I think, charge pumps offer here is they don't have the output inductor of a buck. They have a very small adiabatic inductor, as we mentioned, but they don't have that big, bulky output inductor. So they're not big on height, but also if you think about a humanoid moving around, there's a lot of movement, maybe a lot of impact and vibration. You don't want to have big, bulky components that could cause failure. So I think charge pump could be a very good fit for this kind of application.
Thank you. Last question for you, Laurence, and then you're off the hook. So I really do appreciate it. This has been really illuminating. Well, we could talk about, I understand pSemi recently settled some legal disputes on its power conversion IP, and considering pSemi's portfolio includes, those over 250 plus patents. How does this influence pSemi's market strategy, in your opinion, and as switched capacitor fast charging becomes more popular?
Well, I think what I say, Aalyia, is I say first and foremost, we're a product company. We sell products. We sell innovative products like charge pumps, multi-level, and buck and boost regulators for the LED display market, and that continues. In fact, that's expanding rapidly, as we speak. I think then, secondly, we're very happy that the litigation has been settled. It was settled very amicably. The licensing has been arranged and so on. What I would say is, you mentioned that we do have a lot of fundamental IP in this area. That's a lot of expertise, resources built over a very long period of time, with considerable expense. So we have to protect that IP, and we will robustly defend IP if we feel it's being infringed. So that will remain the case moving forward. But hopefully, again, we can reach amicable solutions with other people in the industry to do that.
Thank you so much, Laurence. I really appreciate your time. This was very informative. Lots of information.
Great.
I really do
Good stuff.
appreciate it.
Well, thank you. Thank you for the opportunity to give you an update from pSemi.